air to water, also from air to glass, or from even water to glass. It's all as long as it's a different material, it'll bend in a slightly different way. This is how it works. The light goes in this direction. Now, if air and glass or water or whatever it might be would be exactly the same, then it would go straight like that. But it doesn't. It gets bent a little bit downward, bent a little bit in. Interestingly enough, if you're shining the light through the glass, it'll actually bend outward when it gets to the air. So people usually don't do this, but when if you look from underwater, out of the water, things would be bent there too. People generally don't do this, and it's not easy to see because when you have water on top of you, it's usually rippling and doing all kinds of things, so it's really hard to tell the effect. But it does. It does, in fact, do that. And in fact, if it comes from glass to air, then there are some properties that are very important. But again, that's really not what we're getting into. The point is that light will bend when it gets from air to glass and glass to air, and it bends differently for different materials. The way it bends is slightly depends a little bit on the wavelength, on what kind of light. Like red light will bend slightly different from green light. So if you want to measure the real refraction of light, what you would do is you would get a specific wavelength light, 589.3. That kind of light. You shine that, let's say, with a laser. Then you measure how it bends, and you'll get the refractive index of that material. Okay, like here we'd use that sodium light, that light goes here. We'd measure this angle, and we can do that easily enough, and we will get the refraction of light of this glass, of that material. So we can tabulate the refractive index of all different kinds of materials: water, glass, plastic, plexiglass, different kinds. The truth is, different kinds of glass, different kinds of plastic will actually have different refractions. There are, like, a diamond has a very different index of refraction than glass, which is one of the reasons that diamonds sparkle a little bit more. They don't sparkle more than the industrial diamonds, but industrial diamonds are not that hard to get. So therefore we don't. They're not as expensive. The only diamonds that we have to pay money, that we have to pay a lot of money for, that people try to pay a lot of money for, those we spend money on them because these are special. These come from slave mines in the African areas, where the various warlords they control these things. Because of that, we spend a lot of money for it, because we only want those diamonds. We don't want industrial diamonds that have the same exact properties. Okay, that's why. I mean, it's just a supply and demand. We have plenty of supply of ordinary diamonds, of industrial diamonds, for example, but we do not have that much of a supply of these what they call blood diamonds. So we only want the blood diamonds. So we're going to spend money on that. That's why they cost so much. But anyway, the fact is that diamonds do have a different refraction, different index of refraction. They bend the light more, for example, than glass. There are some crystalline solids that actually have two different refractive indices. That depends on the angle at which the light hits it. So we're not going to really go into this, except the fact that some fibers actually, I think, also have this. We can identify, like, we match two different fibers, let's say, or two different crystalline solids as being the same or being of the same source if they have both have the birefringence. Because I would say most things do not have this birefringence, so we can like connect the two. If two things have birefringence, it's likely they are the same thing, made of the same materials. Okay, that's as far as index of refraction. We can talk about light as it is itself. So we're going to be considering light as a wave. It does have particle properties. We're not going to be talking about that, just how it works as a wave. White light that we see is not, in fact, only white. It's really the mixture of all colors of the rainbow together. mixed in will give you white light. So when we see white light, we're actually seeing a mixture of all the colors. And we can actually separate them. We can use a prism. When you put light through a prism, you'll see a rainbow. You see, whatever. And this shows that light is actually composed of different colors, which can be separated. It can be separated with a diffraction grating. I'm not going to go into how these things work, but it can be separated from with a diffraction grating. That's when you have a very regular grid, let's say, of things that bend the light a little bit. Well, anyway, never mind. It's a diffraction grating. It does cause the light to be separated into its colors. If you look at a CD, for example, it's because the way the thing is cut, it actually forms a diffraction grating where you'll see the rainbow on the CD because of it actually forms a diffraction grating. Anyway, the fact is that it's split into different colors, and the different colors are different colored because of different wavelengths. Different colors have different wavelengths. We, with our eyes, identify them as different colors, but if we'd be measuring it, we'd really be measuring it as having different wavelengths. When we see something that's colored, when white light shines, the sunlight or overhead light, it's white light. When it shines on something, we see it's colored. What that means is that it's reflecting light of certain wavelengths and not reflecting of others. It's let's say if something is green, that often means it's absorbing all the other colors: the red, the blue, the yellow, and all it can reflect is the green. So it's absorbing the others or whatever it is. It's not reflecting anything except green. So this leads us to the subject of absorption of light. If it's colored, it's likely that it's absorbing some of the light. Remember, the white light has all the colors of the rainbow. It's absorbing some of the colors and reflecting other colors, and together that will make the color that we see. Let's say of green. So things do absorb light. And it's not only true of light, it's true of any electromagnetic radiation, including cosmic rays and radio waves, because they're all part of the same family, the electromagnetic spectrum. This is visible light. It's the rainbow. It's blue and red. It's composed of light of different wavelengths. The shortest wavelength is the blue. It's around 700 or so. That's around 400 or so. Well, it's like purple is more like 400. But anyway, the blue is, let's say, 450 to 500 or so. And the red is like, 800, 700 or so. That's how the wavelength is. It's all part of this whole electromagnetic spectrum, where the wavelength can be large. Here you see it's like a kilometer long. Radio waves can be like a meter. They get shorter and shorter till they get to the visible light. Visible light is on the order of nanometers. That's billionths of a meter. That's visible light. We go further, ultraviolet. That's even shorter. We get to X-rays and gamma rays. Those are even shorter. Those are again. There's even shorter than that, but they're really short. The amount of energy is inversely proportional to the size of the wave. Here, let's take a look at this. Here's like a really short wavelength, right here. Imagine, let's say this is a time period where we have, let's say, 3 of these wavelengths hitting you. So that